In my last video, I explained the focal length of two lenses when they are kept in contact. The two lenses are kept in contact, it can be replaced by a single lens. Now in this video, we are going to see the effective focal length when two lenses are kept at a distance, separated by a distance. These two lenses, when it is kept at a distance, we cannot choose the common optic center. This is the optic center of the first lens, this is the optic center of the second lens. So we cannot choose. So it cannot be treated as a single lens. So actually it is a thick lens, but in one special case, when the object is at infinity, it can be considered as a thin lens. So we have to find the focal length and position of the equivalent lens. These two lenses can be replaced by one single lens. So it's an equivalent lens. So for getting the focal length of the equivalent lens, we should have an idea of the deviation, angle of deviation. So first let us consider a single lens. An object is placed at the point O, a light ray is incident at A and it is undergoing refraction and image is formed at I. Then this is the direction of the incident ray, this is the refracted ray, so this is the angle of deviation delta. Let these angles be alpha and beta. So in this triangle AOI, delta is equal to alpha plus beta, because in a triangle exterior angle is equal to the sum of the interior opposite angles. Then this alpha and beta are very small, so alpha is approximately equal to tan alpha. So tan alpha is PA divided by PO. Tan alpha is opposite side by adjacent side. So since the angle, this PA is very small, so alpha and beta are very small. Then alpha is approximately equal to tan alpha, so it is PA by PO. PA by PO. Similarly, beta is approximately equal to tan beta. Tan beta is opposite side by adjacent side here, so PA divided by PI. So we can substitute for alpha PA by PO, beta we can substitute PA by PI. So delta is PA by PO plus PA by PI. PA, this is height h. Let this PA, so we can write h for this PA. PO, this is optic center. Optic center to the object U. Since it is measured towards the left, minus U plus this PA again h, image distance PI, this is V, image distance V. Since it is measured to the right, positive. H now common, so you take H outside, then 1 by V minus 1 by U. Then as per lens equation, 1 by V minus 1 by U is 1 by F. So delta is equal to H divided by F. For this we can substitute 1 by F as per lens equation. So delta is the angle of deviation, delta. Delta is H by F, delta. Angle of deviation is equal to the ratio of the height to the focal length. A ray of light from a distant object is incident on the first lens. So ray from a distant object will be parallel to the principal axis. First lens produces a deviation delta 1. So it is undergoing refraction. So this is the original direction of the ray, and after the refraction this is the direction. Then angle of deviation produced by the first lens is delta 1. Then again second lens is producing a deviation, and angle of deviation is delta. Then in this triangle, external angle is equal to the sum of the interior opposite angles. So this is delta 2. So this is also delta 2. This ray is extended backwards. Then this is a delta 2. So this is also delta 2. So delta, external angle, can be written as the sum of the interior opposite angles. So delta is delta 1 plus delta 2. You have already seen angle of deviation delta is h by f. So delta 1, angle of deviation produced by the first lens, delta 1, that can be written as h1 by its focal length. So delta 1 is h1 by f1. Generally delta is h by f. Now h1 by f1. Delta 2, deviation produced by the second lens, is delta 2, that is h2 by f2. The net deviation produced by this system of two lenses, delta. So that is so the light is falling on this lens, and this is h1. So for this, delta is equal to h1 by then focal length of the effective lens. These two lenses can be replaced by a single lens. Its focal length is f. So delta can be written as h1 by f, h1 by effective focal length. Then delta 1 is h1 by f1 plus delta 2 is h2 by f2. Now h1 minus h2. So this is h1, this is h2. So h1, this is h2. So h1 minus h2 is P2G. P2 is the optic center of this lens. P1 is the optic center of this lens. So P2G minus P2C. H1 minus H2 is P2G minus P2C. So that is CG. P2G minus P2C is CG. Now in this triangle, delta 1 is approximately equal to tan delta 1, because the angle is very small. So when angle is very small, delta 1 is approximately equal to tan delta 1. Tan delta, opposite side by adjacent side. So it can be written as CG by BG. But BG is the distance between the lenses. So instead of BG, you can write D. So from this, we can get an expression for CG. CG can be written as D into delta 1. From this, CG can be written as D into delta 1. Then for delta 1, you can substitute from this h1 by f1. So you are getting h1 minus h2 is dh1 by f1. So we have to get an expression for h2 by f2. Now you take this to the other side. Then you will get an expression for h2 minus h2 when taken to the other side, h2. Then this you take to this side. So h1 minus dh1 by f1. We have to get h2 by f2. So divide this completely by f2. Now in this expression h2 by f2, we can substitute this. h1 by f is equal to h1 by f1 plus h2 by f2. For this h2 by f2, we can substitute to this. h2 by f2 is equal to h1 by f2 minus d h1 by f1 f2. h1 here common. So every term you divide by h1. So this h1 will get cancelled when you divide every term by h1. So it will be 1 by f is equal to 1 by f1 plus 1 by f2 minus d f1 f2. These two lenses can be replaced by a single lens. So net deviation produced by these two lenses is delta. So the position of this effective lens is here. Now f is the effective focal length, or focal length of the effective lens. So using this expression, we can get the effective focal length. or focal length of the effective lens 1 by that is given by this relation 1 by f is equal to 1 by f1 plus 1 by f2 minus d divided by f1 f2. To find the position of the effective lens, we have to get to P2. This is the distance of the effective lens from the second lens, PP2. PP2, that is equal to EG. But in this triangle, tan delta is approximately equal to delta because the delta is very small. Tan delta is opposite side by adjacent side. So CG by EG. So from this we can get an expression for EG. EG can be written as CG by delta. After rearranging, you will get EG. EG is equal to CG divided by delta. Now CG is H1 minus H2. This is H1. So the CG is H1 minus H2 then divided by delta. But already we got an expression for H1 minus H2. H1 minus H2 is dH1 by F1, where d is the distance between the lenses. So now H1 minus H2 we can write dH1 by F1. Then for delta H1 by F, net deviation is delta. That delta can be written as H1 by F. Then in this expression H1 will get cancelled. So dF by this F can be taken to the numerator. So dF by F1. So PP2 is dF by F1. So there is a distance of the effective lens from the second lens. Then to get the distance of the effective lens from the first lens, we have to find PP1. PP1 is D minus PP2. D minus PP2. But for PP2, we can write dF by F1. Now D is common, so you can take D outside. So PP1 is equal to D1 minus F by F1. So thank you for watching.